All right, I see you started recording. Okay, so if you don't mind, I start with PowerPoint. You know, we are on virtual mode, so, you know, I cannot use a chalk and a board, and so we have to do that. Anyway, okay, let me do this. Okay, so let me share that. Which one? I'm going to share this. Share. All right, and perhaps I even go to full screen mode. You like it full screen or like that? It's good. What do you think?
Full screen, please.
Full screen, please.
Full screen. Here we go, full screen. Okay, I have the pencil. Okay. So this is something what I wrote, which I already mentioned that first week we did something very simple. We looked at properties. We mentioned ideal gas relation and things like that. The only important part was really the shear, which is kind of new, I think so. And we had three things to say about the shear in fluid. First, a shear force in fluid can be present only when the fluid is moving. While in a solid, you can apply shear forces, but if you try to apply it in water, for example, you will slide sideways. So you have to have some kind of a motion. Then I introduced the no-slip boundary condition, where particles near a surface will attach to the solid surface. I said zero relative velocity, but that means that the particles will not move relative to the surface. And then we had the two-plate example. So the particle attached to the upper surface, which is moving, and then stays stationary at the lower one. Therefore, we're developing some velocity profile, which appears to be linear. And then we look at that and we see, oh, Newton's friction law is the shear is equal to the shear, which is du dz of the velocity, of course, and multiplied by some viscosity, which is the mu. And we discussed that. I'm just repeating that. So what I mentioned that this week we'll focus on the equations. Again, this week is going to be, how to say it, more mathematical, but don't get scared. Don't get scared because the big benefit is that we're going to have a roadmap of how to continue the rest of the semester. And again, I said it earlier, examples we're going to do and exams are going to be very simple on a simple case, but they will contain the main properties or the main physics of what we're going to learn. I'm still in the process of repeating some of the things I've done last time. So what kind of equation we can consider? In dynamics, usually you look at equation of motion, which is the conservation of momentum. We can add conservation of mass, and then conservation of energy as well. Now, some people may say that you have a quantity of mass, and then the change of dm dt, change of mass is zero, which is conservation of mass. Then you can take the mass and multiply it by the velocity, which is momentum, and you say the change dmq, and remember q I used for the velocity vector, which is u, v, and w. And the change of that must be equal to the forces acting on the object, which is Newton's law. We can go on and say dmq square dt is going to be energy, and energy is also conserved. However, in a steady state and simple case, mechanical engineers use the formula that q minus w equal delta u, which means that if there is a system, you add heat to it or energy in some sort, then minus the work that the system does must be equal to the change in the internal energy, which is delta U. In simple word, Cp delta T, the temperature will go up. We're not going to deal with that equation, so this is just to mechanical engineers that they can look at that and say, well, there's more equations if you want to use. Then some of the issues now, which coordinate system or how to specify the equations, these were heavy discussion made 100 years ago. And the logical approach would be the Lagrangian, where you try to look at a chunk of fluid and if you can see my cursor right here, this one, can you see the cursor or should I use some pencil? Okay,
I can see it. We're good.
You can see it.
So if this airfoil moves from here to here, but they attach the coordinate system to the frame of the fluid, so the fluid is stationary, then we're trying to look at chunks of fluid. So if I take a chunk of fluid here, then it does all kind of loop like that. It will do a loop like this. Can you believe me on that? I hope so. So anyway, the point is that now I have to have a whole bunch of chunks of fluid here and here and here. And it's not going to be really practical to start looking at all these and what's happening. Again, Bernoulli and all the people in the old days tried to create some kind of particle approach, which is very similar to that one. That would be like dynamics, the Lagrangian dynamics. And you just simply say, sigma f equal dmu dt or something like that, but you have to follow each of these chunks. Now they get mixed up and distorted. It's going to be a mess. The other one is Euleria. Euler said, first of all, let's try to look at the object of interest, like here in this case. So the object of interest is this airfoil. I don't have a very steady hand with the mouse. So what we do is we attach the coordinate system to that airfoil, and then we put a control volume around it, and it will appear that the fluid is stationary. So we just look at the streamline. This streamline is pretty much stationary. So what we need to figure out is some kind of a velocity distribution inside that control volume. Is it clear what I'm trying to mention? Anyway, if I made a good explanation, then turns out that this approach, the second one is, it jumped. Let me go back. The second one with the control volume is the more promising one. And of course, this is the one we're going to use. Okay, now let's go on. Then I kind of made it hard for you last time, and I tried to describe forces in the fluid. So what kind of forces we can, it's not different than mechanics. It's pretty much the same. And let's look at the cube on the left side. Let's look here. Okay, let's look here, this one. Uh-oh. The problem if I use the mouse, then, okay, I have to use the pen again. Okay. I'm looking at this cube. Pen, pen, pen. Okay, this one. Turns out the pen has to be started over in each slide. So I'm looking at this cube, okay? And in mechanics, you try to have this Cartesian coordinate system, and I'm trying to look what kind of forces can act on that fluid. So we had looked at body forces, which is like rho g, and surface forces. Now, this little cube summarizes the surface forces. So, for example, in this side of the cube, which is facing the plus x direction, there could be a pressure. So tau xx, in that case, if I go to this place here, so tau xx is essentially the pressure, okay? And then tau yz, this component, is going to be the force which is acting on the y direction, but on the panel which is facing the x direction. So if I want to summarize all the x directions, then it's going to be this one, it's going to be this one, and it's going to be this one, and they are here. This is the component. So one more time. This will be the pressure. This will be the shear to the x direction acting on the y plane, which is the y plane, which is this one. And then the TXZ would be that one. Some people call it 1, 1, 2, 2. This is just for. And then I mentioned this horrible equation, which is coming from statics or material sciences. And they actually, so what I described here is this. This is in indicial mode. But now they added another term here. Of course, the pressure included there. Here, this is the pressure, which I mentioned, which is the diagonal. And then they added this term, which is a result of, say, there is another cube next to that, and the other cube is being compressed. So if the material is being compressed, then there is shear between the adjacent cubes. So I just want you to look at the equations. We're not gonna look at that anymore. Maybe one more time, just mention it, but that's it. Don't get scared. But you took material course, you have to look at that. So I'm kind of looked at the forces. Now let's look at the practical example. If there is only pressure, like hydrostatic, then say this is a cube in the water, and there's pressure all over it. Then at a particular point, Pascal said that the pressure is the same to all directions. So we're gonna have a diagonal, which is P. Now you're asking, why is minus? Now the minus sign, and we said that before, is a result of the normal vector acting outside of the volume. So, and then the force acting into the other direction. So if I look at this particular force here, okay, which is going to be P times the area, that's the force. The unit vector points to the minus direction, to the plus direction, and the force is going to act to the positive, to the minus direction. So that explains the minus sign. So this is pressure only, no motion. This one is the one-dimensional shear, which we discussed earlier. Okay, we discussed it quite a few times. Okay, so to summarize, we're going to see three types of forces in the fluid. We expect three types of forces. One is going to be the body force. We're going to use only gravity, which acts on the mass. So rho GV, which is rho M, is the force, which is the weight, for example. Could be magnetic forces, could be other forces that act on the volume, the mass, but we're not going to relate to that too much. And then there are the shear forces which exist, so we have to talk about them. Okay, so let's go to the next one. All right, so far I discussed forces and I discussed coordinate systems, and I thought or tried to convince you that the control volume approach makes more sense. Now, another crossroad, what kind of method are we going to use to define the equation? And as I mentioned, there's integral, and we do the integral first, which is much simpler. And then we do the differential, which will end up more complicated, but in a sense, it's the same. We just apply it to a little cubes of elements. Okay, so if you're ready, let us start. So we start with developing the fluid dynamic equations. It is not going to be too complicated. It's a new concept, and then the examples that will follow will clarify all that. Okay, so here's a fish in the river, okay, and it's swimming. We still have the zero velocity boundary condition. We have to look into that. And then I'm just trying to take a chunk of fluid somewhere here. And let's say this is the control volume. Usually we're going to have the whole fish inside the control volume, but not just for simplicity. I just take a little volume here. And when I magnify it, it looks like that. So this surface, which is control surface, okay, the surface of that is a control surface, is fixed in the fluid. And the fluid goes out over it, just passes through it, okay? But the volume is stationary, it's inertial frame, and that's it. Now, this volume has a volume, and it has a surface. And then the first question is, what is the mass flow through that? So, first equation is going to be the conservation of mass. This is called transport phenomena, and I can do the same relation for, say, I put a drop of blue paint, and I want to see how the blue paint changes position and goes through the fluid. That's, for example, anyway, I don't want to confuse you. Let's focus on the matter at hand. So, story is that there is this complex flow, there's a flow over the fish. We pick up an arbitrary point, we put a control volume around it, it's fixed relative to the fish, and it probably has this shape, doesn't have to be rectangular, it's a fixed shape. And it has a surface element, and it has a normal, which is pointing outside of the surface element. Remember that Q is the velocity vector, which is UVW. So I'm gonna do everything in a vector form. Don't get scared, eventually we're gonna explain that. Okay, so what is the mass? Number one. Let me get the pen. Here it is. What is the mass inside the control volume? Question one. Very simple. It's density times volume. Now, if the density is not constant, then we have to do an integral. Okay. Sorry, but that's what it is. If the density is constant, then it's going to be rho times volume. That's it. Very simple. What is the change of the mass? Okay. It's simply that thing with time, dmcv dt. Now, here I said accumulation or, so suppose this thing is fixed in space and then the density is changing. Then could be that more flow goes in than comes out. And then we can think that because of that, there is an accumulation of fluid inside. Okay, so that's basically the wording that I used here. Now, how can I figure out how much goes in and out? What I need to do is find out how much fluid escapes through the boundaries, which is through the surface. So how we do that? We say the change in what goes in and out is really an integral of the velocity, which is normal, integrated by the surface. So it is velocity times the normal, which is normal to the surface. So this is a velocity vector of the fluid. But we're interested in the flow normal to the surface, ds, and then it's going to be q dot n. So that's the vector algebra. That's what it is. So that would be the velocity normal to that surface. And then the area. So the area times the velocity normal is the volume that goes out with time. And then my pi times the density, that's the mass flow rate. Okay, so one more time, the velocity vector UVW, let me put it again, UVW, and this is actually the mass flow rate leaving. So if you don't feel comfortable, I have a more simple example for that. Okay, so I would like to explain that integral term, that one. So, this is not friendly with me. Okay, now I got back control. Here we go. Okay, so this is where I lost you. Let me get the pen. I'm now in a pen mode, so it's good. So this is the term that I put down here, and some of you didn't like it, some of you got scared. Suppose I take this control volume, okay, just an area. Let's say this is an area, and if I want to be more, want to put a more attractive example, let's say this is the exit of a beer tap in the bar. So that's the area, and then the beer comes out at the velocity u, and then the question is how much, what's the volume of the beer that comes out? So my argument is that the volume of the beer is going to be the area times the velocity, and this is per unit time. So this will be the volume of the flow outside. So now let's see how it relates to that quantity. So we said rho, which is the density of the fluid. We said the velocity vector in, okay, here we have the coordinate system, x is the longitudinal one. The normal is pointing positive to the x direction. This is the unit normal. This would be the area, s, okay? And then if I put the vector of the velocity of q is going to be u, because just one direction, no z, no y, and no z. And then the normal vector points to the 1, and therefore the flux is going to be rho US. That's the flow rate per minute. And if I multiply it by rho, that's the mass flow rate. If we look at that, in this case, the fluid is getting outside of the surface. Therefore, this is the mass flow that is leaving. Okay? So if I want to go back to the previous slide, then I say M in, M out. So this is the integral, the positive is M out, but if I want to go how much is going in, then I have to have a minus sign. Okay, so I just wanted to justify the minus sign. So if there would be some fluid going the other direction, that would require a minus sign because of the x direction. Am I explaining that properly, this term?
Yes.
Okay, because if you understand that one, everything else is coming out of this. Okay, so that's what it is. All right,
Sir,
go ahead.
just to clarify, so that term pretty much means the mass flow that's leaving the
Yeah.
control volume.
Yeah, exactly. It's, let's say that how do I relate to that one? Here, I want to find out, let's say this would be a circular element, a circular. Let's say this is circular, and I go here and I say that is the circle, okay? And then at that particular point, the velocity vector is this direction. Okay, let me get the pen. So let's say the velocity vector is this direction, but the surface is actually this. Therefore, the actual velocity vector is going to be only that one. So I have the velocity vector multiplied by the normal here, and multiplied by the area, that is going to be mass flow rate. Are we good with that?
Yeah.
Okay.
Yeah.
Okay, so that's the only difficult part. After that, it's going to be simple. So I'm going back to what I said earlier. So the change in the control volume is what going in and what going out. I don't need to prove anything. That's just simple wording, okay? And then I'm going to place, so instead of that, instead of dmCV, okay, I'm going to replace, and going back. So we said this term is the change, and then the other term is this. So all I'm going to do is put this one, okay, one more time. I'm going to compare each to the one to the other, okay? But now this one actually had a minus sign, okay? Had a minus sign in it, if it's M in minus M on, because what we represent is reduction of the flow. Okay, so dmdCV actually, if I make them equal, then I have to put a minus sign because this represents a loss of mass in the control volume. So I put one to the other, and then I move everything to the other side, and I end up with this. I'm back, okay. If I touch the mouse in that mode, everything runs away from me. So I ended up with this, okay, which is the equation of conservation of mass. Okay, we can rewrite that in another, it's the same equation, I'm copying it, but I say what it means is the loss or the change if the mass inside that control volume is going to be equal to the change in t, with time, plus the change which goes out of the surface. So statement one. Okay, I lost it again, so I have to do the pen again. Pen. So this states that mass is not lost. What happened to the mass is that if there is more going outside or any change, okay, more or less, if any change through the surface must be equal to the accumulation inside the volume. That's it. Okay. So in integral form, I talked about budget, you know, Papa give you $1,000 a month, okay, which is this thing, Oh, this is too sensitive to the mouse. Okay, so Papa give you $1,000. Then you spent $950. And 50 were left in your pocket. So the equation says that money is not being lost. Money, it must be somewhere. It's either you pay somebody or it stays in your pocket. Same thing here, exactly the same thing. Now, this is a very generic rule and it applies to all kind of other disciplines in mechanics and all that. So I just represent that in fluid mechanics mode, but it is good for any other things. And as I mentioned, in economics, you must learn the same rule because money doesn't grow on trees, it just stays constant. Okay, let's go on. So I think that's the hard part. That's it, we finished. So now I need to do, well, almost finished. Okay, so let's go back to where I started. So I try to say that we're going to discuss two equations, the dmdt, this one, here's my cursor, conservation of mass and conservation of momentum. The only problem is that the momentum has the forces, which I started talking about before, and now we have to really take them into account. The good thing is that we can actually do this one very easily. Let me get the pen back. So this term, and I mentioned that this is a change of quantities inside the control volume. It's exactly the same that like we did. So I can take this here and then do exactly the same thing that we did before. All I have to do is add Q here. That's all I did, okay. And then we solved the problem, okay? So very easy, if you agree to equation 1, you should agree to equation 2, okay? Very easy. Now, we have to really take care of the forces. So this is the equation, and then that must be equal to sigma F. Okay, are we good? Somebody show me some sign that you're not asleep. Okay. Yep. Occasionally I have to wake you up because I'm afraid I'm talking to myself, which is natural.
Yeah, okay. We're good.
All right. So again, don't get scared. We'll finish it pretty soon, and then we're going to do examples, and the examples will make it very, very easy. Okay, let me go to the next one. So we need to figure out the forces, and now you got to understand my story. So the argument is that the forces are body forces, shear forces, and now we use the shear only for true shear, like in mechanics, and then we take away the pressure and put it separately. So let me just go back for a moment. Go the wrong direction. Wrong direction. So what are the forces here? Okay, what are the forces? Okay, the pen. So the argument is that there is some mass inside here, and then if say gravity, there's going to be mg. Something like that. If there is pressure, the pressure is going to act on the surface. And then the normal, remember, this is the normal n. So it has to be minus p times some ds. Okay, so that, and then the n is going to give us the direction of the force. So we have to integrate all the pressure terms around it. And also we have to look at shear. So could be some shear where the flow is going like that and maybe inside velocity is less. Then there's going to be some shear force on the surface. So the pressure and the shear will act on the surface. Okay, so let me go back here. And okay, so we had this one, this was the control, and then here we are. So these forces are both shear and pressure. That's how we decide, which is that equation. So now I put the whole thing together. I take the sigma F is this. Before we said that dmq dt, the change of momentum, is this. I'm just copying it from the previous page. And this is the one where I simply added q to the conservation of mass. Okay. And ij, of course, could be x, y, z, or whatever. And then I want to put the sigma f, which is this one. Sigma f, I just put it here. And that's it. That's the equation. And not very useful, but that is the equation in the integral form of the equation, which says basically here that dmq, just a second, let me just write it. I'm struggling with this pen, dt. Okay, go ahead, ask a question. Somebody wanted to ask a question. Question is gone. Okay, I'll keep on going. It will be clarified. So change in momentum in that control volume equal to all the forces which are acting, body and things like that, which I tried to discuss. Let me try to simplify that a little bit so we can understand what we're doing. Oh, first I have a summary. Okay, so here's a summary, which I just said earlier. So conservation of mass. This is conservation of mass. Can you see the cursor?
No, we see a mouse.
Yeah, we can see cursor.
We can see your mouse, yes.
Okay, I use the pen then. Okay, conservation of mass and conservation of momentum. And that's it. It's pretty abstract now, and you may get scared, but we're gonna figure that out pretty soon. So, okay, I think the next one is, okay, all right, here we go. So this is the one that can scare you, and this is the one that I try to make friends with you, okay? So, oh, I actually said, don't worry, in this course we shall focus on 1D examples only. So the control volume thing is pretty good, working well, but we really would like to focus just for the principle, just to understand how this thing works on simple examples. So let's do one-dimensional. What it means one-dimensional. Okay, so the first example is the stream tube, okay, the stream tube. And I would, sorry, and I would like to also explain what is one-dimensional. So imagine, okay, let me get the pen. If I have the pen, then the mouse doesn't trigger. So there is some flow going in here, and I'm gonna capture, could be some sort of a nacelle, could be some inlet. I'm going to put here something and the flow goes through it. So now my control volume is going to be this. This is the control volume surrounding. This is the control volume. That's the control volume. Then I'm going to put a coordinate system here and look at the x direction. This is the x direction. And I really would like to investigate the change of momentum, change of mass into the x direction only, because this would be a solid surface and there's nothing going through it. So all the changes are into the x direction, okay? Then I'm looking, so normal to the surface, for example, here the normal going to be n, but there's no velocity, so probably we cannot talk about it. So the only areas that we have exchange are this one, A1 in section 1, and in section 2. Do you understand the picture? So we have some kind of in a cell, flow goes in and flow goes out. Is it clear?
Yes.
Okay, okay. And then the area is really perpendicular. So the normal for the area is pointing here to the minus x direction. And here it points to the x direction. So let me just clarify that. Area 1, this would be n1, the normal unit vector, which is -1, 0, 0, because it points to the negative x direction. On the out surface, when the flow goes out, the velocity or the normal vector is going to be 1, 0, 0. Very normal, no, nothing dramatic here. Now, for this particular case, and actually for all the other cases in the future, we're going to assume that the density is constant. If the density is constant, we're going to basically remove the first integral. Let me just go back again. So this integral here, for example, if I say this, pen. If I say this, then let's see. I said the volume is fixed because it's in the control volume. So the density must change if I want to have time-dependent flow in terms of accumulation. So we're going to say in the future that we're looking at steady state. Okay, so that's what we're going to do. So one more time, we said incompressible, and then we say steady state, but both are very similar. And then we said one-dimensional, which means that the flow goes only to the x direction. Okay, therefore the conservation of mass, we lost the time-dependent term and we left only with this one. Okay, so now we'll do the same thing what we did with the cylindrical surface, but now we do it for a control volume, for the complete control volume. So the velocity at the entrance is going to be q1. The velocity component x direction is u1, no y, no z. The exiting velocity q2 is u2, 0, 0. Right? Okay. So I'm not lucky with this thing. Anytime I touch the mouse, it jumps. Okay, so let me get the pen back. So I think so far, these things are pretty obvious. It's nothing too dramatic here, okay? Now let's try to write down this equation, which is the conservation of mass. Integral form, steady state, that's it, which we said here. So rho, we said the rho is fixed, and I'm going to look at all the areas. So we have this area which is active, where there's flow going through. Rho, the vector q is u1, 0, 0. The comma should be down here. The normal is pointing to the minus x direction, and the area, I called it A1. I called it A1. Is it clear what I did in that sense? All the other areas, on here, there's nothing happening because there's no flow through. No flow through, there's nothing happening here. So next I have to go here. So here the unit normal is +1. This is the unit normal. And then the area is A2. And then the velocity component is still positive to the x direction. It's the same thing here. So that's the velocity component. I multiply it. Okay, this is a vector algebra. And I end up with this. I end up with this. Because one is plus, this is minus, and this is plus. So I end up actually rho UA equal rho UA, which means the mass flow rate going in must be equal to the mass flow rate going out. This is conservation of mass for this particular one-dimensional model. And it states that the fluid or the mass is not being lost. Whatever goes in goes out because density is constant, so nothing accumulates inside. Is it clear?
Yeah.
Clear.
Okay, so that is very important. If this point is clear, then you guys have a free sailing from here on, at least this week. Okay, all right. So we did the conservation of mass. Now we have to do the conservation of momentum for the same thing. So all we do is we're going to use the same principles. Now we have to massage the momentum equations a little bit. So how are we going to do that? Okay, pen. This is what we developed. This is what I put down there. Okay, and then you had no objections. Then we said that it's incompressible. We lose that term because it's also steady state. Then we have this term, which is very similar to what we have done before. This is the body force. Let's assume that this time the flow is horizontal, and then there is no body force. Here we are. Okay, pen again. Pen. Okay, we cross this term, and then we're crossing this term because we say everything is horizontal. Then we have the shear, the pressure, and then we would like to somehow do something with this one, which is going to be more friendly. So let me do something more friendly. I would say that the pressure here outside, there's pressure PA, it acts on it, but it kind of cancels each other. It doesn't really matter because there's no active area. So the active areas were only here. Now, then speaking of the flow of the forces, we think that there is shear on that surface. Okay, so here's the situation. Here's the situation. There could be pressure in the entrance, could be different pressure at the exit. And because of the different velocities, different pressures, this object wants to move. So now, in order for it to stay stationary, there must be some shear force on that. Shear force, or maybe act the other direction, which is holding it in place. So this would be tau on the control surface. So we think we can take all the shear and integrate it together, and we can call it a force Fx. Okay. If you believe me on that one, then
That's right. Okay.
asking or not believing.
SDSU.edu, it comes to analyze stuff. If there's any questions or information, you can ask them.
Unfortunately, I cannot hear you.
Quick overview in terms of how we're going to be operating. And again,
I believe someone just has their mic unmuted.
You're good. You're good. The last person would like to explain.
Our graduates have
What was that?
really well received.
I cannot hear you. The last person who talked, I could hear him very well. The other with microphone.
So this is where we're starting out in this 12 weeks, and we.
Professor, please mute Benny Jamie.
Okay, you're the one. Please keep on talking because I can hear you well.
It's Benny Jamie needs to be muted.
And our guest speakers joined us already. So Hal, are you there? Here we go.
Hey, Hal.
Benny? Hey, Benny?
We are doing well.
Oh, now I can hear you. Go ahead. What's the question?
I think they just have they have the TV on or something on the background. They're not paying attention.
Oh, so
They might be having on a phone call or something.
Not me. Not me. It's somebody else.
Oh no, it's Benny Jamie. If you look in the participants, I believe it is him that needs to be muted.
PI for the mission.
Oh,
So
okay.
I'll feel free to go ahead and share your screen and we can start using my screen. You can. Awesome. Just need to go into
Okay, so it's not me who's talking. Benny, okay, you want to mute him. I have to find him between 150 students. So there's no question, it's just somebody making some noise, that's it?
Yes, it's somebody doing background noise.
Okay, it's quiet now. Okay, I would continue.
Yes, he is
So
muted.
where were we? So let me just go quickly back. You see, I touched it again. So pen. So this is the equation we had. We tried to throw away the body forces and steady state. We need to clarify this one, which is going to be exactly like before. And then this one is pressure. We'll have to show it, how it is done. This one, we're trying to come up with a story that basically I can replace it with a single force Fx, which is a result of the shear acting on the control volume. Therefore, this equation for our case of the stream tube, I can write it down like this. Okay, so what I have is this is exactly what we had before. I will have Fx, which is the sum of the shear, and then I still have to do the integral for the pressure. Okay, so now let's see. Rho U1, this is on the left-hand side. Okay, so let's go back to the tube. Look at that, that's the one that we're working with, okay? That's the same thing, okay? So pen, so this is at the entrance. I have to multiply by U again. This is the unit normal, and then the area. At the exit, the same thing. The only difference here is the unit normal points out. Also, U2 may not be the same as U1, okay? And then we had this term here, we call it Fx, which is this one. And then let's try to do the same thing with the pressure. So there is a minus sign. Why is the minus sign on the pressure? Because the force is opposite to the pressure, to the normal, unit normal. So we have minus at the entrance here. At the entrance is going to be -1. That's the area. Okay, the normal. Sorry, the normal. That's N1. N1. And then P1. And then we just put a reference number. We take P1 minus PA. PA is a constant, usually to refer to the outside pressure. So instead of taking the absolute pressure, we take what we call the gauge pressure, that's all. And we do it the same way. And then at the exit, unit normal is to the positive direction. We still maintain the minus sign. P2 minus PA and the area A2. If I put all the algebra of these two together, I end up with this. So now, I think I'm going to have a summary, if I remember what I did. But this is the summary of the momentum equation, steady state, incompressible, one-dimensional, the one that we're going to use for examples and exams and so forth. So it's pretty simple. It's one-dimensional. So let me summarize it again. I think I have a next one. Oh, here it is, a summary. Very good. So I expect you to remember that picture, okay? Here is a control volume. Control volume. Flow goes in, comes out. We can identify station 1, station 2, and see what are the differences. We can apply these two rules, which are conservation of mass and conservation of momentum. Conservation of mass simply states that what goes in comes out because there's no accumulation. If density is fixed, you can actually cancel the density, and you can say that, say this is a small area and this is a large area, then the area, the velocity will be related to the inverse of the area. So say small area, large velocity, large area, lower velocity. That's what equation, conservation of momentum, of the mass, very simple. This one states that the force on the control volume is a result of the difference of the momentum going out minus the momentum going in. This will be positive. Remember, there's an x direction. And then the examples will clarify that this is indeed a vector formula. And so this is the change in the momentum. And this is on the sigma forces. This is a change due to the pressure. And then the shear is actually represented here. So that's it. That's the final thing. And I would say that this page summarizes those two equations, conservation of mass and momentum in one dimension, which is the part that I would expect you to understand after I do the examples. Are we good?
Yes, Professor. So the only changing variables in this are the just the area and what else?
Velocity.
Velocity. Okay.
And there could be the pressures as well on the both ends. Okay. And then this is the final.
And Professor, for those equations, this is only concerning a steady state, non-compressible.
That is correct. That is correct. Now, I will say later on a few things about just a sec. Okay, so this is what we need to remember. Now, if we start talking about density variation in these equations, the density is not like in an internal combustion engine where you have a piston and you're compressing it. Density variation in the flow are a result of, say, the flow is going around this object, and because the velocity is changing, then the density will change. We're going to see that for velocities which are subsonic, the density changes are very small. So we did for the liquid, remember we went down 1 kilometer in the ocean and it compressed less than 0.5%. So the changes with rho for liquids are very negligible. In case of gas, if I go back to this example, then the flow really has to be like Mach 0.8, Mach 0.9, that the density of the fluid will change from here to here. Otherwise, it's not. So we can say that, say, if the velocity is less than Mach 0.6, which is pretty fast, we can assume that rho is a constant. Okay, are we good so far? And actually, you can extend that model later on. All right, so let's do some examples. So I know right now it's pretty abstract. Some of you were quiet, some of you took a nap, I'm sure. And somebody was talking over the phone over there. And just let's do some examples, and we have 15 minutes to do some examples. Let's do some.
Excellent.
Okay, let's do simple one. It's again, it's in the book. By the way, I'm following chapter 2, but examples are either from the book or a different one. Anyway, so here is a rocket, and the only change is through the exit. So the only change is the fluid coming out. Here, coming out, there's an area, and there's a, let's say we know about the velocity. So according to our story, we put everything in a control volume. And we're trying to see what are the changes. So the only changes in this area. This is the only area where there's change. There are changes. There are changes. So now we go back to the momentum, the mass flow. So the mass flow is really this. The mass flow rate with m dot is going to be rho u2. So this is how many kilograms per seconds are flowing out. So if you know what is u2 and you know what is the area, then that would be the mass flow rate. Okay, that is this equation. Let me go back to the previous equation. This is that equation here, this one here. First equation in one dimension. Okay, let me going back here. Now, I need to say a little thing about one dimensional, okay? So what we mean by 1D flow?
It's only going in one direction out of the.
Yeah. But 1D flow means two things: is the velocity profile is constant, the velocity is always the same. Okay.
Okay.
Okay. That now for the experts amongst you, you know that the jet will have a velocity profile like that because nobody caught me right now. Because I said that the velocity is 0 at the solid surface. So here the velocity is 0. So therefore the velocity profile must be like that. But when I say one-dimensional flow, and we'll get back to that. I just want to start the training right now. So the 1D flow means that I'm replacing the velocity profile by a one-dimensional velocity which has the equal mass flow rate of the actual more complex profile. So to repeat it, it's the same velocity, but the same velocity everywhere, okay? That's what we call one-dimensional flow. All right? Somebody say hi.
Good.
Okay.
Yeah.
All right.
Hello, Professor.
Okay. Now, I want to take the second equation. The second equation was this complicated, okay? So what we have here, we have, we already got that one. We got this. And then if we do the same thing, we end up, because there's only exit here, we end up that one. And then we're going to have only pressure. Let's say the pressure inside is more than the pressure outside PA. Then we're going to have a pressure term times that. So the force is a result of the change of momentum, which is, if you look at the mass flow rate, this is that one. And this is basically here, this is m dot times velocity, u2, basically, u2. But if there's only one velocity, u2, then we can forget about it. But I put here u2 anyway. So we end up with the force is equal momentum plus the pressure. So that would be the thrust of a rocket. And that formula is actually pretty much used in rocket design. Okay, so this is example one, just to show how simple that formula is. Okay? Make sense?
Yeah, it makes sense.
Okay, let's do another one. Let's make life more complicated. Oh no, this one is for the flux. Okay, we go back to the beer or whatever. So let's say wine. So we have an area here. Okay, we have an area which is, let me get the pen. So this area here is 0.5 centimeters square. Okay, you open the tap, and then the liquid, which happens to be wine, is coming down at 1 meter per second. That's the velocity. So how much is the flow rate? Now we have to, now here we can have two definitions. We can have mass flow rate, which is rho, u, and a, and the area. Or we can have Q, which I call capital Q, which is the flow rate, volume rate, which is just U and A. So in this particular question, how long it will take to fill the 1 liter bottle or the pitcher, then we really, the question is only about the volume. So we don't really need the density. So the volume is really the velocity times the area. So how much is the volume rate per second? It's 1 meter second is actually, 1 meter is actually 100 velocity, 100 centimeters a second. Area is half centimeter square. So it's going to be 50 centimeter cube per second. That's the volume flow rate out of the tap. Okay. If I want to have the mass flow rate, then you have to multiply it by rho. Then let's say it's water. If rho is water, then it's going to be 1 gram per centimeter cube. So it's going to be 50 grams per second, or 50 cc per second. That's what the volume is. How long it will take to fill the bottle? So we have the flow rate, which is 50 cc per second, which we just calculated. The volume of the pitcher is 1 liter, 1000 cc. Divide by 20 seconds. It takes 20 seconds to fill it up. Okay. So this was just to explain the terms. This term, actually, this is what we talked about. So we can have this. And if you want to write down in terms of volume flow rate, then you're going to have U1 A1 equal U2 A2. Okay, so that's for if you're interested just in the volume. All right. So that was a simple example. Let's try to move on. We have time for one more. Okay, let's do one more. Again, this is about volume. So here is something, here are some, maybe a tap or maybe some kind of a faucet pouring fluid into that container, and then it comes out here. So we know that the flow into that container is 1 liter per second. And we see that the flow outside the container is 0.3 liters per second. So how long it will take to fill out the container? It's the same problem. So we have the dimension. So it's pi r square. Okay, pi r square. So what is the volume? Okay, so the volume is pi r square, or diameter square, over 4 times the height, 0.3. So that's the volume of that container. Now the volume times t, sorry, the flow rate times time, how many seconds it takes, is the volume. It's the same problem as before. So the time that it takes to fill it out is the volume, and then the change of the flow coming in and going out. So this is somehow accumulation versus going in, going out. So going in is going to be 1 liter, going out 0.3 liter, okay? And then minus 3 is because liter is actually 10 to the third cc. We did everything in centimeters. Then you put the numbers, it turns out to be 40, almost 44 seconds, okay? So this is again on volume flow rates. I believe we have time for another one. Okay, this is a more complicated one, and it's again a problem not about forces. This is about flow rate. So density is the same, therefore we're going to use only the volume rate. So what the problem says is here, let me get that. And we may not be able to finish, but let me start with that. So the problem states that there is flow going in. Okay, so assume water enters station 1, and average velocity. So we know the condition going in, know the velocity going in. Then we know the velocity that leaves at 3. We know that condition. And then I think we have the area here, but we don't know how much is the velocity. Okay, so that is the question. So now we need to calculate the flow rate going in, the flow rate coming out. So that's the difference. It depends on if it's more or less, we don't know yet. And then the difference will go out or in, we don't know, okay? So what we need to calculate, oh, actually I'm using rho, using water, okay? So, okay, so the mass flow going in, rho UA, it's 1,000 kilogram meter, it's metric right now, I'm doing everything in metric unit. So 1 meter per second, and then 30 centimeters square is actually 0.0030, because 1 meter has 100 centimeters, so it's 10 minus 4. So you do the algebra, 3 kilograms per second, or actually 3 liters per second. That's what's going in at this section. Now we go, what's coming out here? Same story. Okay, same story. Density. Velocity is faster because it's a smaller area, typically. And then also the area is smaller. So it turns out that only 2.4 liters are going out versus 3. So the conclusion is that, yes, we were right, flow is coming out of this area. Okay. How much? Okay, so the difference, 3 minus 2.4 is 0.6 kilograms, no rocket science here. So now how much is the velocity going out? Okay, we have mass flow rate equal rho UA. We just resolve that for the velocity. So the mass flow rate divided by density and then by the area, exit area, and then the outside velocity is equal 0.3 meters per second. So one more time, this is very simple example of using the conservation of mass and calculating the flow rate and eventually the flow velocity. This is one more time, one-dimensional model. I think at this point, I'm not going to put more examples because the next one, I believe, is also about the momentum equations. Any questions up to this point? And I'm trying to convince you that it's going to be fairly simple when we do these type of problems. Okay, let me stop share. Okay, I'm back. And what do you think? Does it sound easy, reasonable?
Reasonable, yes.
Very reasonable, okay.
It seems pretty good, sir.
So I put a whole bunch of integral equations. I hope you didn't get scared. But at the end of the day, they make sense. They may be useful for